All right, let's plunge into a pretty cool phenomenon today. Ice quakes.
Yeah, those tremors that come not from, well, the usual earth-shifting stuff, but from ice.
So we're talking about ice actually having enough force to make the ground shake. Huh.
Exactly. We call them cryoseisms, and they really kind of make us rethink how the earth moves, I mean, it's amazing these things can happen in places you wouldn't expect, like right under your feet.
Like just frozen ground.
Yeah, frozen ground, it's wild. Imagine this. Water seeps into the ground, right?
Okay.
And then, boom, a sudden cold snap hits.
Oh, I see where this is going.
That water freezes. And of course, when water freezes, it expands.
Right.
And all that expansion puts a crazy amount of pressure on everything around it. The soil, the rocks, you name it, like shoving an ice wedge into the earth.
So much pressure that the ground actually cracks.
You got it. And when it cracks, boom, energy's released. That's your cryoseism.
A frozen explosion, kinda. But I mean, it gets cold in lots of places. So is there something more specific that has to happen?
Definitely. Think of it like a recipe, almost. First, you got to have a region that's prone to those like really rapid temperature drops, places where the weather can go from like mild to freezing in a snap.
So quick changes, got it.
Yep.
What else?
Well, think about what's in the ground. It needs to be saturated with water.
Makes sense, like after a thaw or lots of rain.
Exactly. That water's got to be there for it to freeze and expand. And here's a weird one. You need almost no snow cover.
Really? You'd think more snow would mean more likely to happen.
Right. But think about it. Snow's like a big blanket. It insulates the ground.
Ah, so it won't freeze fast enough.
Yep. You want less than 6 inches of snow, ideally, for that perfect ice quake setup.
Okay. So we need soaked ground. It gets cold super fast, not too much snow.
Yeah.
So these things don't happen in the middle of a sunny afternoon, right?
No, not really. Usually between midnight and dawn. Coldest part of the night.
Figures.
And they tend to happen like 3 to 4 hours after a big temperature drop when the ground's really vulnerable.
So if you're in an area prone to this and you hear a loud boom in the winter, it might just be an ice quake.
Yeah, definitely possible.
Now, we've been talking about ground, but what about glaciers? I mean, can they have ice quakes too?
Absolutely. Actually, glacial cryoseisms are on a whole other scale.
You mean like the big glaciers, ice sheets, that kind of thing?
Yeah. The forces involved are enormous.
So this isn't just like a small crack, right? How do those even happen?
Well, picture a huge chunk of ice breaking off a glacier falling into the ocean.
I've seen videos. Pretty dramatic.
Right. It's called calving. And that massive iceberg slamming into the water, it creates shock waves that go right through the glacier.
Like dropping a giant ice cube into a glass of water? Makes sense. Are there other ways it happens?
Yeah. Another way is what we call basal motion. So basically, meltwater builds up under the glacier,
Okay.
reduces friction, and suddenly the glacier can lurch forward.
Wow, so it's like a giant ice sled sliding downhill.
Exactly. And we're talking a sled that weighs billions of tons.
Must create some serious seismic waves. Are there any good examples of, like, these glacier ice quakes?
Oh, yeah. There's one in Antarctica, the Willan's ice stream. This thing releases 2 seismic waves every single day, and each one's equivalent to, get this, a magnitude 7 earthquake.
Whoa, magnitude 7. That's massive. And it happens, like, regularly.
Every day. It moves about half a meter in just 10 minutes. Then it's still for 12 hours. And then, boom, it does it again.
Like clockwork, but with incredible power. So we've got frozen ground cryoseisms and these huge glacial ones. But how do we tell them apart from, the earthquakes we usually think of? What are the signs?
That's a really good question. It's actually really important for scientists to be able to tell the difference because both ice quakes and regular earthquakes, they both can cause shaking, vibrations, even cracks in the ground, but there are some key differences.
So what do scientists look for to tell them apart?
Well, one of the biggest differences you notice is the intensity. Ice quakes are very localized, like their impact is really concentrated around where they happen.
Not like earthquakes. That can be felt for miles.
Yeah, exactly. It's a much more, I guess you could say, focused burst of energy.
So more like a targeted tremor.
Exactly. Another difference is the frequency of the vibrations. Cryoseisms, they tend to produce lower frequency vibrations.
Ah, okay. So it's a different kind of shaking.
Right. It's often so low that some seismic stations, they don't even pick it up. It's more of a deep rumble compared to a higher frequency earthquake shaking.
So more of a rumble than a jolt.
Yeah, good way to put it. And then there's the duration. An ice quake, given the same magnitude as an earthquake, it'll actually last longer.
Oh, really?
Yeah, like a magnitude 5 earthquake might last, say, 5 seconds. But a magnitude 5 ice quake could go on for 30 seconds, maybe even longer.
Wow, that's a big difference. So if you feel shaking for a long time, and it seems to be just in one spot, might be an ice quake, not an earthquake.
Good point. And there's one more thing scientists look at. It's the activity, or actually the lack of activity, after the event. See, after a big ice quake, things usually go pretty quiet seismically, like for hours.
Oh, interesting. So once it releases that energy, that's it for a while.
Yeah, it's like it's let off all the pressure.
Like a pressure valve.
Yeah.
Okay, so now I'm curious, how does all this connect to, the bigger picture, like climate change and all that?
Well, there's a lot of research going on right now, and it's looking like there might be a link between, the fact that ice quakes seem to be happening more often, especially the ones from glaciers, and climate change.
So as temperatures rise and glaciers change, are we seeing more of these glacial earthquakes?
There's definitely evidence that suggests that. For example, in Greenland, there's been a pretty concerning increase in glacial earthquakes in the last few decades. And of course, that's also when temperatures have been going up and the ice has been melting faster.
So these ice quakes, they're like a warning sign.
It's possible. You could think of them as kind of a window into what's happening inside glaciers, how they're changing, and the data that scientists are collecting, it's showing some interesting stuff.
Like what kind of stuff?
Well, they're seeing changes in how often the ice quakes happen, how strong they are, where they occur. All that can give us clues about how glaciers are reacting to things like warmer temperatures and melting.
It's pretty amazing, but also kind of scary. How do scientists even track all this, though? Do they just put a seismometer next to a glacier?
Huh. If only it were that easy. It actually involves a whole global network of seismic stations.
Wow, so they're listening to the whole planet, basically.
Pretty much. They have to sort through a ton of data to find those ice quake signals. It's like looking for a needle in a haystack.
And they can actually tell where an ice quake happened, how strong it was, all from that data?
Yep. They've got these sophisticated algorithms and techniques. It's pretty cool, actually. It combines geophysics, glaciology, all sorts of different fields.
So we can use ice quakes to monitor climate change, but are there other uses? Like, can they help us predict anything or maybe prevent some kind of disaster?
That's something scientists are looking into, definitely. See, as glaciers melt, they can create some pretty unstable situations, and that can be dangerous for people and infrastructure nearby.
In what way?
Well, there's this thing called a glacial lake outburst flood, or GLOF. Basically, there are these lakes that form near glaciers, and they're often dammed by ice or rock. But if that dam fails,
Uh-oh.
yeah, a massive amount of water can be released, and that can cause catastrophic flooding downstream.
Sounds terrifying. So could ice quakes give us a warning about these GLOFs?
There's research suggesting that they might. Remember we talked about basal motion, how a glacier can suddenly lurch forward? Well, sometimes that can destabilize the dams holding back those glacial lakes.
I see.
So by tracking ice quakes, especially the ones related to basal motion, scientists might be able to spot areas where there's a higher risk of a GLOF happening.
So it's like an early warning system coming from the glacier itself.
Kind of. It's still early days, but the potential is there. And this is especially important in places like the Himalayas, where there are a lot of glacial lakes.
Where the risk is really high. This really shows how important it is to understand ice quakes. It's not just some abstract science. It can directly affect people's safety.
Exactly. And it reminds us that, what happens in these icy parts of the world, it does matter to all of us. It's all connected.
So what's next? What are the big mysteries about ice quakes that scientists are still trying to figure out?
Oh, there's tons we still don't know. One of the big things scientists are working on is trying to create better models that can actually predict when and where ice quakes will happen.
Models that could link those tremors to, like, the bigger changes happening in glaciers and what that means for us.
Yeah, exactly. We need more data.
Yeah.
We need to really nail down the physics behind it all.
Yeah.
And then we can use that to build tools that can actually help people make decisions. Like, imagine being able to predict a GLOF based on ice quake patterns. That could save lives.
That would be incredible. So ice quakes could actually help us deal with the effects of climate change, not just understand them.
Exactly. And it goes beyond prediction, too. We're finding out that ice quakes might even be playing a role in how fast glaciers melt.
Really? How so?
Well, when they happen, they can create fractures in the ice, weaken it, and that can make it melt faster.
So it's like a vicious cycle. Ice quakes are a sign of climate change, but they might also be making it worse.
It's complicated, that's for sure. But it shows that the cryosphere isn't just sitting there passively reacting. It's an active part of the climate system. And if we want to figure out how to deal with climate change, we got to understand these kinds of interactions.
It makes you realize just how interconnected everything is. What about the future of ice-quake research? What are scientists excited about?
Well, one thing that's really cool is all the new tech that's being developed to study the cryosphere. Things like remote sensing, AI, all that stuff.
So we can basically get a better view of what's happening in these remote icy places.
Yeah, it's like having a new set of eyes to watch over them, to really see how they're changing. But it's not enough to just observe, right? We have to use that knowledge to do something. We have to reduce emissions, help communities adapt, keep investing in research.
It's a call to action, for sure. And it underscores that what happens to the cryosphere, it affects all of us.
Well, I have to say, when we started this deep dive into ice quakes, I had no idea how far it would take us.
Me neither. It's been quite a journey. We've gone from tremors in the ground to giant glaciers, talked about the science, the impact on people, the whole ethical dimension. It's a pretty fascinating story.
And it's not over yet. There's still so much more to learn.
Absolutely. But every new thing we discover, it brings us closer to understanding how our planet works, how the cryosphere, the climate, and our own lives are all connected.
Well said. And thanks to everyone for joining us on this deep dive. We hope you'll keep exploring the amazing world of ice quakes because they really do have a lot to tell us about our planet.